All right, hi everybody, and welcome to the May MAPP program webinar. Today the topic is Drought Research, Improved Understanding, Monitoring, and Prediction of Drought. I'm very excited about the speakers that we have today, and thanks the three of them for taking the time to do this on a Friday afternoon. We're almost at the weekend, so congratulations to everybody on that achievement. So we're first going to hear from Krista Peters-Ledard from the NASA Goddard Space Flight Center, and then we'll hear from Rong Fu from University of Texas at Austin, and then finally from Chunzai Wang from the NOAA AOML. And we're going to be kind of cascading from monitoring to understanding / prediction to understanding of drought as we go along in today's section. So, hopefully it's an interesting narrative for everyone on the phone. And thanks everybody for calling in. So, Krista, are you on the line?
I'm here.
Okay, great. I'm going to transfer control over to your computer and then just share your desktop.
Great. Okay. Everybody can see that?
Good, yeah, so whenever you're ready, go ahead.
Okay, thanks. Yeah, so as Dan mentioned, my talk is oriented towards drought monitoring. So we have been working for the last several years with the NLDAS team at NSEP EMC to demonstrate the impact of terrestrial remote sensing observations on drought monitoring. And we have a paper that's now in press that's referenced below our co-author list. And please refer to that paper for any details. That paper deals with soil moisture and snow depth assimilation. I'm going to just briefly review that today, and then I'm going to talk about some newer results that we've just been working on. Okay, so there's basically been three different land data assimilation experiments oriented towards NLDAS. I'm assuming most people on the phone know what NLDAS is. Just briefly, it's the North American Land Data Assimilation System. It's now going into operations at EMC, and this basically runs multiple land surface models over CONUS at an 8th degree resolution, and it uses a common set of forcings or inputs. So what we did for our work was we used the same inputs, the same forcing, and we ran the NOAA version 3.3 model for the snow and the soil moisture assimilation experiments. And then we have a new assimilation experiment I'm going to talk about today with a new model that's not yet in NLDAS, known as the catchment land surface model, and that's been developed here at NASA Goddard by the Global Modeling, the GMA, the Modeling and Assimilation Office. So there's two different data assimilation methods that were used in these experiments. For the snow and the soil moisture that are discussed in that paper, that uses a 1D ensemble common filter. For the GRACE assimilation, actually it requires a different approach, and for that we use a 3D ensemble common smoother. All of this has been done with our land information system software. I can give you more information later if you want to know more about it. And for all these runs, we go back and run for a retrospective period back to 1979, and then we start assimilating whenever the data is available. So for snow and soil moisture, that would be with Aqua's AMSTER E, which starts in 2002, and for GRACE, we start in 2003. Okay, so those are the basic experiments. So this is a quick review of the results from our soil moisture and snow depth data assimilation results from the paper. So if you remember, some of you have seen this before, but just the bottom line is that we first did assimilation evaluations where we evaluated the impact of the soil moisture on the soil moisture in the surface and root zone using point data like SCAN to evaluate that. And it's, the most challenging part of that evaluation was that the change in the anomaly correlation was quite small. We did similar types of evaluations for snow, and in that case, it's tricky because we actually use the GHCN data to bias correct the path of microwave retrievals before we assimilate, and so we can't compare to the in situ data. So instead, we compare to either the SNODAS system or the Canadian model analysis. And what's interesting is that the Canadian model tends to be bias low and against the HCN data, and the NODAS tends to be biased high. And so when you compare to both of those, you do show some improvement, but it's hard to know whether it's really better. So we chose to do some evaluations against a completely independent variable, which is stream flow. And so that's what this one figure is showing. And I know it's hard to see, but I'm just going to give you, it's just a summary of the results. So we used 3 different metrics, which are what we call normalized information contribution metrics. And these metrics look at the change in either RMS error or anomaly correlation or the Nash-Sutcliffe efficiency. And they look at the change due to assimilation. So what we're looking for is to show you warm colors. So the warmer colors indicate an improvement in this metric. The cooler colors indicate a degradation. So if you look at the 2 columns, the column on the left is the change in these normalized information content metrics due to soil moisture assimilation. The right column is the change due to snow assimilation. You can see in some areas there's improvement, in some areas there's not, and then there's histograms of these metrics shown all the way to the right. And as we discussed in the paper, you can see that there's certain regions where there's clear improvements, especially in the Mississippi, the Missouri, and the Red Arkansas. And there's other areas like in the West where the snow in particular just doesn't seem to go so well. So what we did after we convinced ourselves that the stream flow looked better, then we decided we would trust the assimilation and we would look at the impact on drought. And that's shown as an example in this slide. So if you're familiar with the U.S. Drought Monitor, the way drought monitoring works in the U.S. is that we have these categories of drought from D0 to D4. So each one of these time series plots you're looking at from 2000 to 2012 shows you a time series of the area over the U.S. that was classified at that drought category. And so you can see there's certain times where large fractions of the U.S. are classified in drought, and you can see how it varies with time. And you can see as you look down D1, D2, D3, the more severe drought obviously has less area associated with it. And the different colored lines indicate the impact of assimilation. So we did our drought monitor in black, and then we looked at the open loop, which is no assimilation at all. That's green. And then there's blue and red lines, which show impact of soil moisture or snow assimilation. And the bottom line is that there's times when, the soil moisture in particular has a positive impact. The snow impact, we couldn't really show much. And some summary statistics for anomaly correlation, RMS error, and bias are given on the right. So without going into detail, we found it was sort of a mixed bag. There were times when it helped, times when it didn't. And so we're continuing this line of work. In the next slide, what we decided was, as I mentioned, the snow was one of the problematic parts of that initial study. So more recently, we have been working on some refinements to snow data assimilation, where we actually use the IMS, or the MODIS snow cover area, to condition the assimilation. So you only assimilate where IMS and MODIS agree with the with the existence of snow, so that you kind of prevent putting snow where it shouldn't be, and so on. And so, again, like I was mentioning before, you've got two things you could compare to that are independent, CMC and SNODAS. So the top row is CMC, the bottom row is SNODAS. The column on the right is RMS error. The column on the left is RMS error. The column on the right is bias. And I think if you focus in on the biased ones, it kind of tells the story, where the open loop, generally, it depends on what you compare to. You tend to have a high bias if you compare to CMC. You have a low bias if you compare to SNODAS. In general, the biases get better when you assimilate, and they get even better when you add the SBA. The next slide, I think, is probably more interesting, because we kind of mentioned that it's difficult to have a known reference for snow. So we looked at stream flow again as an independent variable. And so the top on the left shows if you assimilate the passive microwave only and what the improvements are. And this is that same normalized information contribution. This one is is specifically for the Nash-Sutcliffe efficiency, which is a typical metric for stream flow, sort of goodness of fit type parameter. And then the bottom one shows the impact of the passive microwave, DA2, plus either MODIS or IMS. And you can see, again, when there's more warm colors, it means things get better. And the difference plot showing you the difference between using the MODIS and IMS and not using it, you can clearly see where there's big blocks of red all over the map, where it makes a huge difference. So we think that this is kind of the way to go, and we're working on this as something to transition over to the NLDAS team so they can actually start assimilating, and that'll feed into their operational NLDAS and the NLDAS drought monitor. Okay, so the last piece of results I want to show you are these GRACE, terrestrial water storage results. These are new results. These are not reported in a paper yet. So like I mentioned before, you've got a new LSM and a new DA method. And again, the first step we do is we always look at the ground, the state variable that corresponds to the variable that we're assimilating. So in this case, we actually use USGS groundwater well data. So each point here is not a stream flow, it's actually a well. And we're looking at the anomaly correlation and RMS error for the well data. And you can show that the data assimilation is improved relative to the open loop. Go to the next slide. Similar sorts of results where you see the open loop. This is for soil moisture. So in this case, you've got point measurements of soil moisture, and you're asking, how does the terrestrial water storage assimilation help you get a better soil moisture? So in this case, you can see across the board in the column all the way to the right that the DA TWS column is better than the open loop, the OL column. Okay, so again, we go, we're satisfied with that, so then we go and look at the stream flow using the same metrics I already explained. And again, here you see areas where there's large improvements. There's areas, kind of a mixed bag, improvements on the West Coast, upper Mississippi, and the Northeast. Other areas like the Southeast and the lower Mississippi and Texas don't seem to show improvements. Okay, so with terrestrial water storage, if you don't know anything about that, I can't explain it in too much detail, but it's an integral, right? It's an integral of all water storage change. So it's part of it's due to groundwater, part of it's due to soil moisture, and part of it's due to snow. So here we're looking to see if it improves the snow. And in fact, in this case, right now it looks like we're not able to show much improvement in the snow. So we're trying to figure out that now against the GHDN. Against CMC and SNODAS, there's definitely areas in the western U.S. where it is much better, so that's encouraging. This one's a little tricky. This is fluxes. So there's 4 different flux products that cover CONUS, and there's questions about which is the most accurate. But in general, here again, red is good. So you can see against Alexi, which is one of the products that's been also funded by the science team in the Drought Task Force, we do show mostly improvements except around the Great Lakes and upper Midwest region. Okay, finally, getting to the drought, these are the last couple results. The percentiles here, just like I showed you before, except now these are from 2003 to 2013. And the only thing to notice here is that the open loop is green, the terrestrial water storage assimilation is blue, and I think the biggest thing compared to the previous results is that the change due to terrestrial water storage assimilation is quite large compared to the open loop. So before, I think the sensitivity was pretty low to some of the soil moisture and snow assimilation, whereas with terrestrial water storage, it's a big sensitivity. The bad news is in some cases there's degradations, especially at the higher drought categories, and so we have to figure out what that means. But for some of the categories, there's improvement. So this is a very new result. So we're still not sure where this is going, but it's interesting that all of the other variables seem to indicate improvement, but when you get to comparing to the drought monitor, we can't show significant improvement yet. Okay, and then just some case studies to give you some examples of what this looks like spatially, so you can get a better sense for it. 2006, 2011, and 2012 droughts, and on the left is no terrestrial water storage assimilation. On the right is with storage assimilation, and the summaries are kind of below where, you know, it helps in some places, and, you know, it helps not only with location but with severity. In other cases, you know, there's misses, so we've got to look into that more. And then the last result is this one, which is, this is just some statistics showing you over each region where the improvements are. And we think the most interesting one is in the Northeast. There seems to be systematic improvements in all the drought categories. In some high drought categories in the high plains, Northeast and West, there's improvements as well. So the orange bars being the ones with the grace. So I think my time is up, and I'm going to conclude with this slide, which is, you know, just a summary that, you know, from our paper in, that's in press now in JHM, the soil moisture and the bias-corrected snow depth tends to improve the soil moisture snow depth and generally improve stream flow with some improvements in drought area, you know, and there's some nuances about when and where those improvements are. The newer snow data assimilation definitely shows potential for using the MODIS and IMS SDA to further improve the snow, and we have not yet investigated the impact on drought. And then the last result I was just showing, which is with the new LSM, they show that the GRACE terrestrial water storage data assimilation definitely improves groundwater soil moisture and snow in some areas as well as stream flow. And like I mentioned, the drought area is very sensitive to the GRACE data assimilation compared to the snow depth and soil moisture with, you know, what I just mentioned, these marginal improvements over some categories, but in the Northeast, you know, improvement everywhere. So there's definitely regional differences in whether GRACE is helpful or not, and we will keep exploring this in our new projects that we're going to be working on with, you know, with the NLDAS team. That's it. Thank you.
That's great, Krista. Thanks a lot. There was a lot of, you know, very impressive results. And unfortunately, I gave you short boundary conditions on the timing there, so sorry. There's a lot of good stuff there. So I just sent a message to all the attendees that if you'd like to ask Krista a question, please send me a chat message. So if you go to the top of your screen, you'll see that you can select chat, and then you can send a message to the host, which is me, and we can unmute you. You can ask Krista a question. I haven't received anything yet, so Krista, if you hold tight, we'll just see. People might be typing something in right now, and if not, we'll move on to the next speaker.
Okay, thanks.
Okay, so not seeing anything. Krista, thanks a lot for the interesting presentation. I appreciate you taking the time to talk today. Next, we're going to move to Rong Fu. Rong, are you on the line?
Yes. Can you hear me?
Yeah, sounds good. So I'm going to transfer control over to your computer.
Okay. Share my desktop. Okay. Are you able? Can you see my screen?
Yep.
Okay, great. Okay. So I'm going to present our preliminary result that aim to explore mechanisms that's behind the spring to summer drought memory over the U.S. Southern Plain, and also explore their application to the for early warning of the summer drought over U.S. Southern Great Plains. So the question here is, the research question we aim to address is why do some La Nina events appear to lead to summer drought, whereas others do not? And what conditions that separate these two different La Nina? And we often turn to soil moisture memory, especially during the spring to summer period. But we don't know whether there is true soil moisture memory. If so, how important is such memory in determining the summer drought? What processes is responsible for such drought memory? And finally, we'd like to know whether if the spring to summer drought memory did exist, whether it will be helpful in terms of provide early warning of summer drought. So the data we use are mainly NAR and NCAR reanalysis and CRU precipitation, and also this merged soil moisture product. And these are mainly used for mechanism diagnostic study. And then we use the CFSR and also CFSV2 for training the statistical model for the summer drought early warning. And so the first question we'd like to explore is why do some La Nina events lead to summer drought where others do not? We did a composite analysis, look at the difference between the La Ninas that followed by summer drought over southern U.S. Great Plains versus those La Ninas that did not follow by summer U.S. Drought over southern Great Plains. So on the left two column, this shows the wind and the wind anomalies, difference in 700 millibar wind precipitation for DJF and also for March, April, May. As you can see that there is stronger anticyclonic circulation for those La Ninas during the winter, for those La Ninas that followed by summer drought. And also this anticyclonic anomalies seem to persist into March, April, May. And if you look at the sea surface temperature difference between these two types of La Ninas, and one difference standing out that is warming over the North Tropical and the North Atlantic, and this has occurred both in winter and the spring. And so this so how does this anticyclonic anomalous anticyclonic circulation influence rainfall? And I would like to point out is this anticyclonic circulation could be a result of increased rainfall to the east of the East U.S. as a result of warmer SST anomaly over the Atlantic Ocean. So to explore how does this anomalous circulation influence rainfall and convection, we did a composite analysis for convective inhibition energy, and as showed by red curve in this left top panel, or right top panel, and versus the convective inhibition energy of non-drought year over the southern Great Plains. As you can see that for the drought year, you see a very strong increase of the convective inhibition energy during the spring from March to even to June, and versus non-drought year where you actually have a much weaker thinning in spring. So what might cause this strong increase of convective inhibition energy? And it's besides the surface dryness, in fact, the increase of temperature at the top of the boundary layer at 700 hectopascal also played an important role in increase of convective inhibition energy. So because over southern Great Plains, during the spring is the transition of main source of rainfall. This is a transition between extratropical synoptic disturbance generated rainfall in winter and early spring to thermodynamic driven convection during the late spring and the summer. So this increase of convective inhibition energy could basically suppress the onset of summer thermodynamic driven rainfall. And so you can see the persistent in both rainfall and the soil moisture from spring to summer. The bottom 6 panel shows that these rainfall anomaly over southern Great Plains, especially Texas, persists from early spring to late spring and the summer, and you see also persistent soil moisture anomaly, negative soil moisture anomalies. And the question is whether this persistent surface dryness, drought memory, if you will, is due to the low frequency, remotely forced large-scale circulation change, or contributed by the feedback, atmosphere feedback to the soil moisture dryness. So before we move into discussion of the mechanism, I would like to show a little bit of statistics. And we actually look at how many summer drought events can be linked to spring dryness during the past more than 100 years. And so among 13 out of 16 severe to extreme drought over Southern Great Plains are linked to spring dryness. Only 2 dry springs did not lead to summer drought. So this is really in contrast to a dynamic model, which you couldn't maintain the initial soil moisture for more than 2 months. So now we explore what mechanisms that contribute to this persistent dryness. And so first of all, we look at the lead-lag correlation between the soil moisture anomalies and the 500 hectopascal geopotential anomalies, and compare that to the autocorrelation of the 500 geopotential hectopascal anomalies. So here, the red curve shows the lead-lag relationship between soil moisture and the 500 geopotential hectopascal anomalies. And the lead phase suggests the soil moisture lead the 500 geopotential hectopascals. As you can see that during the soil moisture anomalies is significantly correlated with 500 millibar positive increase of 500 millibar geopotential height 10 to 20 days later. And this correlation is greater than the autocorrelation of the 500 geopotential hectopascal itself. So which suggests that soil moisture anomaly might might contribute to the 500 geopotential hectopascal anomaly, the positive one. So how does soil moisture anomaly or land surface anomaly contribute to influence the large-scale circulation anomaly? So to explore this question, here we look at the domain averaged humidity, specific humidity at the top, and the geopotential high anomaly in the middle panel, and the vertical velocity in the bottom panel. And this is a domain average over Southern Great Plains and the vertical profile of them as a function of time during 2010 and 2011. So the shade indicate the spring season. You can compare the 2011 spring season to 2010 spring. So as we can see that this is the atmospheric specific humidity has been low since the previous fall. And during the spring, and the green, you see very little green, which indicate deep penetration of the moisture, and which is an indication of the convection. And you also see quite strong positive anomalies of geopotential height in the middle and the lower troposphere that's linked to this large-scale anomalous anticyclonic circulation. And you also, from vertical velocity, you actually can see not so much mean vertical velocity, but the lack of a strong uprising motion in spring. And there is also indication of due to surface dryness, even when you have a strong synoptic activity, that gives you deep, very deep low pressure system. But you don't really see a deep penetration of the moisture, which and also suggests that you see, I'm sorry, you actually, so you see vertical velocity, you see very deep, low pressure anomalies, but you don't really see a deep penetration moisture, which suggests the surface dryness perhaps suppress convection even when you have a favorable synoptical conditions. And in addition to directly influence on precipitation, we also want to look at how soil moisture influence large-scale anticyclonic circuit, contribute to that, and also influence large-scale subsidence. So we know that beyond synoptical scale, the large-scale subsidence is mainly driven by diabatic cooling. And during the drought, the negative diabatic cooling anomalies can be a contributor both by decrease of latent heat release due to decrease of rainfall, also contribute by increase of long wave cooling, relative cooling. And the question is, what are the relative importance between the increase of relative cooling versus decrease of latent heating? So to explore this question, we computed the diabatic heating and relative heating anomalies for the 2011. So here the purple line indicates the total diabatic heating anomalies. As you can see, they're negative. And the black curve shows the anomalies of long wave cooling, which is stronger as expected from decrease of cloudiness and also atmospheric humidity. And of course, the decrease of cloudiness is compensated by increase of solar radiation. So the net relative cooling is determined by difference between increase of long wave cooling and increase of solar heating. During the January to April, the total diabatic heating anomalies is primarily contributed by the increase of long wave cooling, and the decrease of diabatic latent cooling, latent heating due to decreased rainfall has a minor contribution. And during the summer, May and June, the decrease of diabatic heating is primarily due to the decrease in rainfall, which leads to decrease of latent heating. So this result, preliminary result, really emphasize the importance of the radiative cooling linked to water vapor and the cloud feedback to surface soil moisture in spring. So the last question is it possible to provide an early warning of the summer drought based on anomalous condition in summer? Okay, I'm almost done. Let me quickly. So the reason we would like to explore this early warning using spring condition, early warning summer drought using spring condition is because the climate model has pretty good skill in predicting winter and the spring circulation, but has larger uncertainty in predicting summer circulation. As showed here, even when you look at a 500 joule potential hectopascal joule potential, and you see large discrepancy between model and observation. This is for CIMP 5. And so the question here is, can we use dynamic prediction in winter and spring and the empirical model to improve assessment of summer drought? So I'm going to, given the time limit, I'm going to skip detailed analysis. So we basically use the multivariate EOF and also the canonical correlation analysis to train this statistical model using the CFSR and also for the period of 1982 to present. So this figure shows the correlation between predicted 6-month SPI in July and observed 6-month SPI in July for the Southern Great Plains domain, and versus the autocorrelation between April SPI 6 and July SPI 6. And as you can see that this predicted, if you will, empirically predicted SPI 6 and shows better scale than the autocorrelation. And I'm just putting this figure from Guan et al. Shows that a dynamic model could not predict, could not beat the baseline, the autocorrelation. So real quick, and the probabilistic prediction is even better. This is the two alternative forced choice test, and shows around 60 to 90% of agreement. And also when we look at the prediction for below and above normal rainfall, the agreement is also between as high as 60 to 89%. So I'm not going. So these are just a case showing the prediction versus observed. And finally, I would like to just show real quick that based on this empirical model, this empirical model predicts a wetter condition over the southern plain, especially southern Texas, versus the dynamic prediction. And it will be interesting to see which one is turn out to be the case. And finally, summary. Most of the La Nina do not lead to summer drought over southern Great Plain, and the anomalous anticyclone circulation in spring and the resultant dry soil moisture anomalies appear to be critical in set the stage for summer drought over the southern Great Plain. Strong spring soil moisture deficits can reduce convection, cloudiness, and atmospheric humidity. The resultant increase of long-wave cooling could have a stronger contribution to subsidence and the middle tropospheric high anomalies in spring than the latent heat reduced due to rainfall deficits. And such relative feedback, along with the soil moisture rainfall feedback, could further reinforce the initial large-scale dry circulation and the soil moisture anomalies, consequently maintaining the dry anomaly from spring to summer. The empirical model hindcast shows it seems to shows better scale than the autocorrelation, and therefore using the spring to summer soil moisture memory could provide additional predictability for improved summer drought assessment relative to that provided by SFT alone. And so again, I think the the most interesting result coming out of this analysis is the importance of the cloud water vapor feedback, relative feedback to the drought anomalies during spring to summer. And we have not been really pay attention to these processes. So perhaps this is something we have been missing in our study of drought mechanism in the past. Thank you.
Okay, thanks a lot, Rong. Any questions from attendees on the phone line, please type them into the chat feature and send it to me, and then I can pass it along to Rong. I'll unmute your line. So, is there any questions here for Rong? So, Rong, I'll just hold on for a few seconds. Somebody might be typing something. Okay, I'm not seeing anything yet. If anybody's typing something, we can come back to it at the end. So feel free to, send it along. Rong, thanks a lot for the talk. I'm going to move on now to Chunzai. Chunzai, you're on the line. Chunzai, are you there? We can't hear you. You might need to unmute your phone.
Hello?
Hi, Chunzai.
Yep. Can you hear me?
Yep, I can. So I'm going to transfer control over to your computer right now and then just share your desktop with us so we can see your screen.
Can you see it?
Yeah, it looks great. So take it away whenever you're ready. Thanks, Chunzai.
Okay, I'm ready. Okay. Hello, everyone. This is Chunzai Wang from Miami. And today I will talk about the impact of the Atlantic warm pool on North American rainfall. First, what is the Atlantic warm pool? In 2001, we published our first paper about West Hemisphere warm pool. We defined the warm pool by acid T larger than 28.5 degrees C. You see that the warm pool basically has two parts. One is over East Pacific, and starting in March and peak in May, and in June, East Pacific warm pool decay. At the same time, in June, Atlantic side warm pool starting to develop, and further develop, and Atlantic side warm pool peak in September. And in this study, we focus on Atlantic side warm pool. We call Atlantic warm pool. And this slide shows SAT composite for Atlantic warm pool. Top panel shows large warm pool, and low panel shows small warm pool. And you can see the warm pool has a large variability, and large warm pool are almost 3 times larger than the small one. And the question is why we want to study the warm pool. The first, we know the ANSO impact on the climate mainly in winter, and we need additional information for summer climate prediction. And this is the priority season for Atlantic warm pool region. So ANSO is not enough. And the second point is Indo-Pacific Ocean and Indian Ocean compete with each other. Atmosphere response is response to the interbasin anomaly. We cannot make a climate projection based on Pacific only. And another point today I will show you is Atlantic warm pool is very important because warm pool affect both North American rainfall in cold season and warm season. However, the mechanisms are different. And another point is warm pool is very important for Atlantic hurricane. And the last point is moisture transfer from warm pool is also important to the tornado activity in central U.S. The last 2 points, this topic I cannot present today. However, we published some paper in these 2 topics. Today, I will focus on the rainfall, warm pool impact on the rainfall over North America. We first take a look at the observation. So here, what we did is we performed multiple regression of rainfall and the sea level pressure onto Nino 3.4 index and Atlantic warm pool index during the cold season. And the cold season is defined from October to March. Top panel shows ANSO impact, and low panel shows warm pool impact. The shading is rainfall regression, and the contour is sea level pressure regression. So we first take a look at the ANSO. We focus on the North American region. You see, we have a strong positive rainfall regression during the cold season. What does it mean? This means that when we have a La Nina in Pacific Ocean, the South U.S. rainfall will increase. We have a La Nina over Pacific Ocean, the rainfall over South U.S. will be decreased. This is consistent with the previous result. For the sea level pressure response, you see that low pressure in North Pacific, high pressure over Canada, and low pressure over South U.S. This is the PA pattern. For the warm pool, we see that the rainfall impact over South U.S. and the Southwest U.S. Rainfall is decreased, which means large warm pool will decrease rainfall over South U.S. and South U.S. and the small warm pool year, the rainfall will be increased. This is during the cold season. Now, how about a warmer season? And this figure shows similar multiple regression of rainfall at sea level pressure. However, during to the warmer season, from April to September. Again, top panel show ANSO impact, and low panel show warm pool impact. So during the cold warmer season, the rainfall over North America is not significant. And for the warm pool impact, we show that negative rainfall regression over central U.S., which means large warm pool will reduce rainfall over central U.S., and small warm pool will be increased rainfall over central U.S. This is the opposite. And then in this study, we try to use a couple ocean atmosphere model to study the warm pool impact on the rainfall over North America. what we did here was first calculated SAT anomaly composite for large warm pool and small warm pool. And then we run the couple ocean atmosphere model for 1,500 years. Then we perform another 3 group model line. The first line is called control line. What the control line is? The control line is the ocean atmosphere is full coupling, except in the warm pool region. In warm pool region, we relax model SAT to the model climatological SAT. And then we perform another group line, so-called large warm pool line. And ocean atmosphere a full in coupling, except in warm pool region. In warm pool region, we relax the model SAT to climatological SAT plus the large warm pool composite we calculated early. And similar situation for the small warm pool, where we also perform small warm pool line. Then we take a difference between large warm pool and small warm pool as the warm pool response. So here is the result. Here it shows the model rainfall and sea level pressure to respond to the warm pool. Top panel shows the cold season, and low panel shows the warm season. And again, the shading is the rainfall at the contour the sea level pressure response. So what we see during cold season over southwest U.S. and south U.S., the rainfall is decreased. So this is consistent with the observation I showed you earlier. And the sea level pressure response shows high pressure over North Pacific and low pressure over Canada and North American and high pressure over South U.S. This again the PA pattern. However, during warmer season, the rainfall pattern is a little bit different. You see the big difference is over central U.S., which means during warm season, the rainfall over central U.S. is decreased. This is it. Then we also perform the moisture budget for the large warm pool and small warm pool line. Now here we show the cold season. The left panel shows the rainfall, and the right panel shows the moisture flux divergence. It's like this, mathematically like this. And you see the two patterns are very similar, which indicate the rainfall is mostly controlled by moisture flux. Then we can divide the moisture flux term into 2 terms. One is the so-called change by mean circulation dynamics. Another is the change by thermodynamics. And the top equation shows the mean circulation dynamic change, which had 2 terms. One term is induced by wind divergence change. Another is due to the moisture advection term. The similar situation for the thermodynamic will have 2 terms over there. Then we make a plot. And here it shows the mean circulation dynamic part. If we compare this panel with this panel, the pattern is similar, which means moisture flux divergence is most due to the mean circulation dynamic change. And because the mean circulation dynamic change had 2 parts, this part and this part, we see it, and this part and this part is dominant, which means mean circulation dynamic change is due to the wind divergence change. So the conclusion here is during the cold season, and the wind divergence change is very important for rainfall over North America. Then next we take a look at the warmer season. Warmer season from April to September. Again, rainfall, moisture divergence, you see the pattern is similar. Again, the moisture, the rainfall is controlled by moisture divergence term. And then again, moisture divergence term is controlled by mean circulation dynamic change. However, it's different from warm season. From cold season is during the warmer season, the moisture advection term is dominant. So the conclusion here is during the warmer season, moisture advection by wind change is very important for rainfall over North America. Okay, so we try to show that during response to warm pool during warm season, cold season very different. During the warm season, response is local. However, during the cold season, response to warm pool is remote. So here what we plot is the baroclinic and barotropical stream function. So basically the baroclinic stream function represents local diabatic heating, as shown early by Gill in 1988. And the atmosphere teleconnection is the most can be seen from a barotropical stream function. We'll first take a look at the warmer season. This is warmer season. Top panel shows the barotropical stream function, and lower panel shows the baroclinic stream function. We see that the baroclinic stream function is much stronger than the barotropical stream function, which suggests during warmer season, warm pool induce a local change, which then change wind. However, during winter time, the situation is totally different. What we saw here, we see here is that the top panel is the barotropical stream is much stronger than the baroclinic stream function, which suggests the removed effect is very important. You see that bottom have show high pressure over North American, low pressure North Pacific, and low pressure over North American, and also a high pressure over South U.S., which is exactly the PA pattern. So here during colder season, warm pool induces the change in Pacific Ocean. Then Pacific Ocean change to teleconnect to influence over the southeast rainfall. Then here we first take a look at the during warmer season local response. Here what we plot here is the moisture transporter at 30 degrees north. Here is the high, here is the longitude, and the top panel shows the control line, and lower panel shows the model line between large warm pool and small warm pool case. You see we have during control line we have a strong northward moisture transport, which this is associated with the green plain low level jet. And for the difference between large warm pool and small warm pool, we see the strong negative value, which means warm pool will reduce this northward moisture transport and then reduce rainfall. And this is the difference between large warm pool and small warm pool can further divide into three terms. So the first term is change due to the medium unknown wind. This term. Second term is a change due to humidity, and the third term is nonlinear term. So if we compare this panel with this three panel, the dominant term is this term, which means the medium unknown wind change is the dominant for the total warm pool response. So conclusion here we can get is a large warm pool reduce gray plain low level jet, which decrease northward moisture transport and reduce the rainfall over central U.S. during the warmer season. However, during colder season, slightly different. Is the atmosphere response, remote response to the Pacific, then influence the rainfall over U.S. So large warm pool induce cold SIT anomaly in tropical Pacific, which teleconnect to influence rainfall over North American during colder season. What we show here is the ocean atmosphere response to the large warm pool, small warm pool. Here, top panel shows the SIT, the shading, and vector the wind, and low panel shows sea level pressure response to the large warm pool. So what we see is that the tropical ocean response is a cold SIT anomaly. The question is how large warm pool induce this atmosphere ocean response over Pacific? This is our next question we want to answer. So what we did here is this: because Atlantic warm pool is peak during summer. So what we did, we first plot the velocity potential and diverging wind at 200 millibar during summertime. So top panel shows the control line, lower panel shows difference between large warm pool and small warm pool. So we see that when warm pool during summertime is larger, this warm water induced atmospheric convection, which produce regional Hadley circulation. So you 200 millibar. In 200 millibar, the wind is a flow from warm pool region to the southeast Pacific. For the warm pool effect, this one large warm pool will increase this regional Hadley circulation. So the point here is the large warm pool will increase regional Hadley circulation, which then increase change the ocean atmosphere over Southeast Pacific. Here is the detail. What we want to see is here is SST and heating flux and the wind from July to November. The left panel of SST, the left panel is the latent heating flux and wind stress. So as I said, warm pool is larger during summer. So large warm pool will change the increase regional Hadley circulation. Associated with this Hadley circulation is the cold SST over Southeast Pacific and southeast wind and negative heating flux over Southeast Pacific. And after this, the local ocean atmosphere feedback will further increase the SST anomaly over Southeast Pacific. For example, during the August, southeast wind anomaly is stronger, and this stronger southeast wind anomaly increases evaporation. And this increased evaporation further increases the cold SST over Southeast Pacific. And this feedback is so-called wind evaporation SST feedback. And this feedback repeat and further to the winter. During winter time, the tropical Pacific SST become colder. So the point here is the summer warm pool induce the cold SST anomaly during winter over tropical Pacific Ocean. So this cold SST anomaly over tropical Pacific Ocean will induce PN pattern which influence the rainfall over North American. And here is the result. So here is again our model result. The top panel shows the gel potential head at 200 millibar, and low panel shows gel potential head at 850 millibar, which shows there's a high pressure over North Pacific and low pressure over Canada and high pressure over Southeast U.S. And this high pressure over South U.S. will reduce the rainfall over there during winter time, during the cold season. So here is a summary this talk. So basically, during warm season, the large warm pool lead a gale-type atmosphere response, which will weak North Atlantic subtropical high and reduce northward moisture transport, and then reduce the rainfall over central U.S. However, during cold season, situation different. The large warm pool effect is slows warm pool induced change in Pacific. So basically, a large warm pool will induce the cold SST anomaly in tropical Pacific, and which this cold SST anomaly will induce the PNE pattern, which reduce rainfall over South U.S. The opposite is true for the small warm pool. So I stop here. Thank you for listening.
Okay, thanks a lot, Chunzai. So if anybody's typing a question in, we'll wait a few seconds for that. In the meantime, since we're past 3 o'clock here, I'll wrap up a little bit. I'd like to thank the speakers, Krista, Rong, and Chunzai, for taking the time to tell us about their work this afternoon. We have another webinar coming up in June. It's going to be the last webinar in this year's series of MAPP webinars, and the topic is reanalysis. Last year, from the MAPP call for proposals, we funded a number of new initiatives in reanalysis, and we're going to hear during this webinar from Gil Campo, who's out at the NOAA Earth System Research Laboratory, as well as Arun Kumar from the NOAA Climate Prediction Center, and some of the work that they're doing to advance reanalysis research before NOAA launches into next generation reanalysis products. So it should be a really interesting webinar, and I hope that everybody will join. We don't have a date for it yet, but stay tuned to the website, cpo.noaa.gov/map/webinar, and we'll post the date on there. We'll put the slides up from this webinar as well as a recording on the website, and you can access recordings from all of the previous webinars from this season as well as the last 2 years if you'd like. There are a variety of different topics that we cover every year. So I haven't seen any questions on the chat feature. I think people are ready to go home for the weekend, so let's do that. I am really appreciative of all the speakers taking the time today, and thank you to everyone who attended. I hope that it was an informational and interesting webinar for you today. So thanks a lot. We'll talk to you in June.